Dr. Boualem Djehiche amongst us. Boualem is a professor of, I think, let me just give me 2 seconds here, professor of mathematical statistics at the Royal Institute of Technology in Sweden. And he has published widely in mathematical finance and insurance mathematics, and has worked on using quantum techniques on types of insurance contracts. And I think you may well talk about that today, actually, also. Yes. Boualem, the floor is yours, please.
Thank you. Thanks, Emmanuel, for having me. This is a nice opportunity to talk to specialists about a pedestrian approach to use a quantum computer to model, or at least to say something about insurance contracts. So an insurance contract compared to a financial one is much simpler. At the same time, it can be very difficult to price. There is no so we don't have access to data like market data. So the goal of this exercise was basically to check whether a quantum computer can can compete, or at least can beat AI or neural network models that are widely used. I will mainly introduce very simple model, recall a bit what is a quantum computer from my point of view, and how can be used to model these ABT insurance contracts. The main, so this is a pedestrian approach, an approach by a beginner, although a beginner who has a strong background in probability. So I'm really chasing probabilistic concepts in this quantum jungle. So what is a health and disability insurance? So it is just, as you may know, provides economic protection from illness or disability. Typically, an insured individual receives a monthly payment from an insurance company in the case of illness. The expected cost should be covered by premium payments. The insurance company needs to predict future costs using statistical models based on historical data. So I insist in introducing all these steps because each of the steps needs to be correctly mapped to the quantum paradigm afterwards to make this computation useful. So typically, this estimation or prediction is typically done by estimating transition probabilities between states, such as healthy, ill, dead, and so forth. So it looks like modeling a Markov chain on a quantum computer. So here is the basic model. So the basic model consists of a population of insured individuals. EI is the number of healthy individuals from population subgroup I. The I is the number of individuals that fall ill amongst the EI insured. And DI is simply modeled as a random variable following a binomial distribution with probability PXI. PXI is the probability that an individual randomly selected from EI falls ill. What is XI? This is the most important information. So XI is a data set that belongs to RD in our case here, which may contain information about age, gender, etc. And the whole goal is to estimate PXI given historical data. So what we propose a support vector regression, which is easy to understand, and it is widely used. to model logistic disability inception probability. So we take the logit of Px, and we want to write it as a linear combination of alpha I, and the kernels plus beta. So K in our model is a quantum kernel estimated on a quantum computer. The parameters alpha I and beta subsequently fitted using SVR. So what we propose a hybrid quantum classical learner, and the functional form we have should guarantee that Px belongs to 0, 1. Okay, so this is the disability model. So we are chasing a kernel K that we can estimate on a quantum computer, and now we will try to map this data to the quantum setup. So xi and yi's are observations in a data set. A feature map from the set RD to a Hilbert space F maps a sample data point X to a feature vector. And for me, this is a crucial step, because I can map a vector of D points to the set of probability measures by just taking the empirical distribution, 1 over n, the sum of delta, the Dirac mass at the xi's. But here it is preferred to look at it to have this mapping to Hilbert space with some inner product. So phi naturally gives rise to a kernel through the relationship 1, where kz xz is similarity measure between x and z in the feature space. Now, once we have k, so we can construct the reproducing kernel Hilbert space associated with phi, following the recipe 2. What is important here is that fx, which is the scalar product between a weight phi w and phi x, can be seen as a linear model in the feature space. And this is probably the key observation, which means that we can use this paradigm to solve a regression model in a quantum computer. So the classical way to solve to find this, let me go back to this, to find alpha A, K, and beta, or is just to minimize, to use this to formulate it as a convex optimization problem, where the xi's are slack variables. So epsilon determines the error tolerance of C and of the solution, and C is a regularization parameter. Of course, this is plausible. This is more or less linear quadratic with nice constraints. So its dual formulation is better, because it links the maximization to a kernel K. And both solutions coincide and are given by f of x being the linear combination of alpha I, k, x, xi plus beta. So this is a very simple model. And now we try to figure out what can we do with that model. So the feature map and thus the kernel can be chosen in many different ways. So there is a famous classical kernel, the Gaussian kernel, that works well, of course. A modern alternative, hopefully, may be provided by a class of quantum kernels. So what we do here, we map the data to quantum states in some quantum feature. and quantum kernels can be estimated using quantum computer. So we tested this very simple model on quantum computer, and we also compare it with what we know, because this is a well understood model in the literature. So quantum computer, I will just describe how a quantum computer works. I know that you know that, and I apologize for repetition, and this is due to the fact that I wanted to stress the way I think of this process. So quantum computer is governed by laws of quantum physics. In classical computer, the information is represented by bits, taking values in 0 and 1. For quantum computer, these qubits, that means all linear combinations of zeros and ones, as specified. A quantum state induces a probability distribution on 0, 1. And this is one key result for me as a probabilist. So at measurement of quantum state of the qubit, an outcome is determined. Okay. So the state of a qubit can be represented on the Bloch sphere. And you see, you as a quantum physicist or specialist of quantum mechanics, you see it as a nice transformation, rotation around the x and z axis and so forth. This representation is in fact very important, because the Bloch sphere helps me to determine conditional probabilities. And this is probably, I haven't seen this interpretation in quantum computing books. So programming a quantum computer with the qubits is performed by creating quantum circuit A, or script A. Script A induces a probability measure of a random variable V on 0, 1 to the power D here. So running the circuit A essentially means sampling from V. And for me, this is exactly, so now I'm back to my mother's street. So this is very appealing to probabilists, statisticians, actuaries, and quants. So how this works. So the quantum feature, as I mentioned before, is a map that maps a set of data points to a quantum state in a Hilbert space H. And quantum state should solve the Schrödinger equation that can be represented by the recipe 5 or the recipe 6. And here comes the tricky step. It is not at all trivial to represent a number of data points in RD with a wave function. That means it is not really trivial to find H. I can give you an example. I just take a Markov chain with two states, 0 and 1, or -1 and 1, right? So the generator, or the Q matrix of this matrix, or the Q matrix of the Markov chain, is a 2 by 2 matrix whose rows are very special. So the first row can be written as -A and A, where A is non-negative, and the second row is B minus B, where B is non-negative. So the closest Hamiltonian to a two-state Markov chain should be the Pauli Hamiltonian, right? But the Pauli Hamiltonian contains the off diagonal of the Pauli Hamiltonian is a complex number. And the transition from the Q Markov chain, the Q matrix of the Markov chain, of the generator of the Markov chain, to the Pauli matrix is not trivial at all. For the Brownian motion, it is much easier, because we know that H is just the Laplacian plus a potential. And if it satisfies some growth conditions, then the recipe 6 is well defined, and we obtain a salvage joint operator and so forth. So this is one issue that is raised from a modeling point of view. So for every pair phi and x, so we have the feature and data points. So we associate the unitary group, the feature embedding circuit, and the kernel is given by recipe 8. Okay, so the kernel is just the norm of so this is the value of the norm of scalar product phi x phi z, and can be written like that, right? So what we implement in the quantum computer is basically the recipe given by equation 9. So that is kxz is given by the probability of obtaining the measurement outcome omega 0. That is the ground state when measuring the quantum state psi defined by recipe 9. And this is basically the end of the story if we have a good representation of the number of points by the quantum feature map. So the kernel can now be estimated. We load the state psi xz into a quantum circuit. The circuit is run n times. Kxz is estimated by the frequency of the ground state, right, measurements. So the form 8 that we mentioned is exactly what a computer, quantum computer should do. And this is what we implemented in this small exercise. So we go back to our disability model. So we want to use a quantum kernel to be defined. That is to be able to estimate the parameters alpha, I, and beta, so that we can match the data with the model, right? So this regression model is very popular in neural networks. So instead of so this is just it can be represented as a neural network of just one layer, and usually it is enough to get a very good fit. Okay, so how here is what we do. So we our data, we have gender. So gender, so it is xi1 and age xi2. So we choose the kernel set with the unitary group defined by this one. And equation 10, this is exactly the kernel that is the unitary operator that is obtained by interpreting the Bloch sphere, the elements in the Bloch sphere as transition probabilities. So Ry denotes the rotation around the y-axis of the Bloch sphere. CRZ denotes the rotation around the z-axis for the second qubit, conditional on the state of the first qubit. And as far as I can see, so this is the key link between quantum computers and all probability calculations, including those in finance, like Black-Scholes or Heston model or any other type complicated fractional Brownian motion and so forth. So the unitary operator 10 that we can be represented by the quantum circuit like this, and I'm sure that you know that, right? So the circuit is designed to clearly separate male and female subgroups, because we have to deal with the health and the disability insurance for where gender is very important component. Gradually increase the dissimilarity between different age groups as the difference in ages increases. Okay. So for each pair xi and xj, we run this quantum circuit, inserting the values of xi, and then run the adjoint circuit, inserting the values of xj. And this is very simple one. So we start with 0, 0, and create all these transition probabilities. We perform the simulations on the IBM Yorktown quantum computer. This simulation was performed continuously since COVID. The IBM Yorktown computer suffers from hardware errors, a lot of hardware noise that disturbs the estimation. But hopefully it will be better in the near future. So for each pair Xi and Xj, we run the circuit 8,192 times and measure the outcomes. So this number is just, we just use the capacity that we are allowed to, we have access to as non-specialists. So we estimate the kernel K of Xi, Xj with the observed frequency of the ground state. And we use the binomial sampling error. So this is, it is small. And we know that the hardware error dominates. So the results we obtain are compared with exact classically determined kernels. And this is what we do. So this I hate these two pictures, but I will just leave them. So this is the concrete result. So the red dots represent females, the blue represent males. So the dashed line represent females, state vectors that are estimated using classical techniques, and the continuous lines are those produced by Yorktown quantum computer. And you see, despite the hardware noise and errors and so forth, so the quantum computer or the quantum algorithm performs much better, surprisingly good. This is the statistical evidence for that. So leave one out cross-validation. So we use weighted out of sample R squared for classical quantum kernels. So classically polynomial kernels give rise to an R squared that is, it is 55%. State vector quantum kernels perform surprisingly well, 54%. Gaussian kernel that is used to be perfect gives 52%, and Yorktown kernel gives 51%, and the classical or the sigmoid neural network using sigmoid functions performs, and the linear perform worse. So this gives us, in fact, a hint that quantum computers or quantum computing techniques reveal to be very efficient. So in an ideal world, if we have a hardware that is less noisy and stable and so forth, this is concrete evidence that they will outperform all these machine learning techniques, regenerative, what's called the both reinforcement, using reinforcement techniques using reinforcement learning. That means whenever we have an optimization problem, we try to learn the optimizer or the optimal strategies and so forth. So this is a good news for at least Emmanuel, who is very enthusiastic to quantum computing, and with me as well, right? The problem here is, as I mentioned before, is in solving the non-trivial problem of linking quantum features to quantum states, or the data to quantum states. And to me, it is not really, it is a very hard problem. So basically, if we want to so this is an open question. So you have a Markov chain that describes the movement of a discrete market, discrete asset, and the price of an asset in discrete time. So what would be the corresponding quantum features or the corresponding unitary operator that would be useful. Once we know that, I think all the pricing of structural products, derivatives, and all that becomes easier. Up to now, I haven't seen any answer to this question for simple Markov chains. I looked at somehow a bit the literature in the early 90s, where people tried to devise a quantum Markov chain or quantum chain by playing with the annihilating and the operators and using the Bose and fermionic decomposition and so forth. But this is a paradigm. So this is language. They fail to give a concrete example of a simple two-state Markov chain represented with these models. Probably I'm too harsh, but I think it's nice to provoke thoughts in this direction. So what we did, so we propose a hybrid classical quantum approach to estimate estimate disability inception probabilities. We suggested the suggested model performs similar to existing classical models, even on noisy hardware. The approach is not restricted to insurance applications and can be used for general regression and classification models, especially credit risk, fraud detection, and so forth. So hopefully this small contribution it gives a warm and positive message for jumping or using these techniques. Scheduling problems related to health or operations or chirurgical operations in hospitals is a nightmare for standard computers because it is an NP-hard problem. Probably it can be solved with a quantum computer because the difficulty is in the fact that difficulty is the curse of dimension, and although all the steps are of linear programming type. This is a set of references that I like very much, and would like to thank you for your attention. I'm sorry that I just used a very short time to give my presentation, and that's it. Thank you.
Thank you very much, Boualem. Thank you.